Hello, folks. So today we're going to be looking at molarity, concentration, and the calculations with regards to that. So let's go ahead and get started. So, uh, in the previous videos, we've only considered reactions with solids, but not all of our things will be in solid form. A lot of times it'll be a lot easier to deal with them in liquid form. Some things it's almost impossible to get in pure solid form. A lot of acids will be in liquid mixtures called solutions. But some things are incredibly toxic in high concentrations that would be present in solid form, so we store them in solution. But what do we do and how do we deal with it? What if we mix it into a liquid? How do we deal with it? So, real quick, a refresher. Remember, a solution is what occurs when we have a mixture where a solvent, the proportion in larger quantities that does the dissolving, dissolves another substance, which we call the solute. Now, we could be dissolving a solid into the liquid. We can dissolve the liquid into the liquid. We can dissolve gas into the liquid. Technically, solutions don't even have to be, the solvent doesn't have to be a liquid. We could have technically a solution of gas into a solid, or there's various different things, and we can talk about them like for example, fogs and gels. But for the most part, we will focus entirely on liquid solutions. But one of the key features is the homogeneity of this mixture. The idea is that you're not getting just one little bit of it mixing in, it mixes in the whole bit. As we can see over here in the picture down there, that we have high concentration of red dye, and we're slowly moving to more and more dilute. It's getting to a point where it's only pale red at the far end of that, where there's very little red dye. But the fact is, there's red dye throughout, and it's spread out. So it's not just a clump of red at the bottom, it's all mixed in. Now, these mixtures are essentially a ratio of solute to solvent. The way we talk about this ratio is called the concentration. So, the concentration. And we'll talk about the math involving that in a couple slides. In the meantime, some other terminology. If we say this solution has a low solute to solvent ratio, so there's a lot of solvent, very low solute, we say this is dilute. A solution with a high solute to solvent ratio is called concentrated. You might have some concentrated cleaning solution where it's a lot of active ingredient, and you might spread it out into multiple different bottles by diluting it. So you take a little bit of the, like say, you need to polish the wood floors, you take a little bit of the concentrated floor scrubbing solution and add some water, and then it goes a lot farther, and it's not as powerful. So that's just a quick reminder. So with that in mind, we have to introduce a new unit. You may have seen this unit around, but you may not have. This unit is called molarity. Breaking it down, so molar, it has to do with moles. But this molarity is given the unit of capital M. Both when used in an equation as a variable, it will be M, but also as a unit itself, it will be capital M. Always capital M. Not lowercase m. We might see this later, but lowercase m is another unit. Now, much like many other derived units, this comes from the putting together of two separate units. That molarity is the ratio of moles of solute over liters of solution, the volume, moles per volume. So please note that the liters of solution includes the volume of the solute. When you mix these two together, the solvent and the solute, we get the solution. So we're looking at the total volume, the moles of solute over the total volume of solution in liters. So I will often interchangeably use capital M or moles per liter. They both mean the same thing. Now, because this is a ratio, if I scale up one unit and I scale up the other unit by the same portion, it still gets the same. However, as a metric unit, if I scale up only one unit, it will change. So like if I did millimoles of solute per liter, I would have millimolar because I divided by a factor of 1,000 on the top in the numerator, but not in the denominator. But if I divided by a factor of 1,000 in both, in the case of millimoles per milliliter, the two factors of 1,000 cancel each other out. So it's still 1 molar. So always be cautious of that. But we can always do this. It's always a ratio, so we can scale this up infinitesimally. 1 molar solution could be 1 mole in 1 liter, or 2 moles in 2 liters, or half a mole in 500 milliliters, which is a half a liter. When you do that simple ratio, you always get 1. So real quick, practice. If I have, what is my molarity if I have 3 moles of sodium hydroxide in 12 liters? What about if I have 0.35 in 500 milliliters? So I don't really need to do this, but we'll do this. We'll jump to the doc cam real quick. So, since molarity is defined as N over V, which is defined as mole in liters. So if I have 3 moles and I divide by 12 liters, it would give me units of moles per liter, which is equal to molarity. 3 divided by 12, 3 goes into 12 4 times, so we have a factor of 1 over 4, which is equivalent to 0.25 molar. So 1 over 4 is the same as 0.25, so you have 0.25 moles in a liter or 0.25 molar. Either answer is equivalent. Now let's look at this. 0.35 moles in 500 milliliters. Now, a liter and a milliliter are not the same. So if I want to get molarity and not millimolarity, I need to convert milliliters to liters. There is 1,000 milliliters in 1 liter. That unit cancels. So with that in mind, 0.35 divided by 0.50, this becomes 0.70 M. So this guy, even though it has less moles, ends up being more concentrated because it's in less volume. The idea is it's always a ratio, and so we're comparing moles to liters. Yep. Now, oftentimes we will not be just directly calculating molarity. We will have to deal with this. We will often in lab have to make solutions. And this process of making a solution, especially by adding more water, is a process called dilution. We're going to change a concentrated solution into a dilute solution by adding more solvent. This is the easiest thing in the world to do. You just add more solvent and mix it up to make sure it's homogeneous. Now, this is how we'll often need to do things, because you'll have a stock solution. You'll often buy something concentrated. It's cheaper like that. However, it's more dangerous like that. So we'll take a small portion out and then we'll dilute it into a larger, more useful volume. Because the stores aren't necessarily going to know what concentrations you're going to need, so they're going to make it in only set amounts. Like if you're buying vinegar from a store, you can either buy it in typically 5% active ingredient or 10%. They're not going to have 8 or 7 or 3 or 1. They're going to have those two. If you buy it from a chemical supply store, you might be able to buy it at max concentration, which I'd have to check at. Try to remember. It's like 95%, maybe a little bit less, maybe a little bit more. But so there's only comes in a couple set concentrations that you can typically buy, and so if you want anything outside that range, you'll have to make it yourself. In the process of dilution, there's one thing we must always keep in mind, that as we add more solvent to the stock solution and we dilute it to a new molarity, the moles of our solute, so the amount of atoms in the stock, does not change. It does not change. If I have a mixture of fruit, some apples and some oranges, the apples are my solute, the oranges are my solvent. If I throw in 3 more bags of oranges, the amount of apples I have do not change. The total amount of fruit has gone up. The likelihood of reaching into that pile of fruit and grabbing an apple at random has gone down. However, the total number of apples in the room has not changed. So when we make a dilution, please note the moles of our solute are not changing. Only the ratio. Only the ratio. So with that in mind, we can set up 2 equalities. The equality that the moles before the dilution, our moles concentrated, are equal to our moles after the dilution, our moles diluted. If these two things are the same, and by rearranging of the molarity as moles over volume, that I can get molarity times volume equals moles, I can set 2 sets of molarity and volumes equal to each other. Now, the subscript is only a descriptive term that helps us remind what numbers we're dealing with. I do not need a descriptive term. I can just use simple numbers, as you'll see. The molarity of the concentrated solution times the volume of the concentrated solution must equal the molarity of the same dilute solution times the volume of that new dilute solution. So the other way to look at this is M1V1 equals M2V2. The molarity and volume of situation 1 must equal the molarity times the volume of situation 2 for that same solution. And that's because the moles have not changed. So hypothetically, if I have 25 milliliters of a 1 molar sodium hydroxide solution, and I were to add enough water, it would be 75 mils of water in this case, to make it 100 mils. Please note, I do not need to factor in the 75, I just need to factor in what is my new volume. So 1 molar times 0.025 liters equals the molarity of situation 2 times 0.100 liters. And if I do that and I rearrange, and how do I solve for my M2? Well, I have to divide both sides by my 0.1000 liters. And if I do that, my new molarity has changed to 0.250 molarity. So the basic idea is I have M1 V1 equals M2 V2. The hardest part of this is making sure you understand what is the ones and what are the twos. So what volume would I need to dilute to turn 50 mils of 5 molar to 1 molar? Now let's once again go to the .cam. That's why I have it here. I have it here for this reason. So these guys are related. So this is, we'll say this is our V1. This is our M1. We want to know the volume. That's our V2. So this must be our M2 because that's the descriptive concentration. So I can turn milliliters to molarity, or I can get my answers in milliliters. Either one works. But let's show this how this works in the unit-wise. Remember, molarity is a mole per liter. So 5 moles per liter times 0.050 liters equals 1 mole per liter times volume 2. So I'm going to get that to the other side. So we have 5 moles 1 liter times 0.050 liters times 1 liter per 1 mole equals volume. So 5 times 0.05. What volume would we need? We would need, I have to write this over here, 0.250 liters or 250 milliliters. I'm doing that math kind of fast, but I'm just multiplying by that ratio so now that I have it defined. I said you could leave it in milliliters and you'd get your answer in milliliters, because liters would cancel liters just fine, as this liter would, that milliliter could carry over. Now, calculating molarity from mass. So oftentimes we will not already start with a solution made. You might have to make your own solution. How would we go about doing that? Well, you need moles. So if you're making a solution, we're going to take our mass and we will convert this into moles, and then we can calculate molarity. Alternatively, if we start with molarity, we can use our molar mass and our moles to figure out what weight would we be delivering of our compound. So if I spray this with sugar water and I know the concentration of the sugar water, I can figure out how much sugar are we delivering. So these two examples, 34 grams of FeO in 1.4 liters and 3.2 molar of H2O2 in 67 milliliters. Again, we got to go back to the document camera. I mean, yes, I could absolutely just click the next, but that kind of defeats the purpose. I'm trying to show you how we're going to go about doing this. So iron. Iron is 55.85. Oxygen is 16. So the molar mass, 55.85 and 16 is 71.85 grams per mole. So, starting with 34 grams of iron oxide, we're going to multiply by 1 mole of iron oxide over 71.85 grams of iron oxide. The advantage of that is grams and grams will cancel. Then, to get units of molarity, I need moles per liters. So I need to divide by my ratio of 1.4 liters. That would give me moles and liters. Or you could just find your moles and then N over V is molarity. So I take my 34 and I divide by my 71.85 because it's on bottom. Then I divide by my 1.4 because it's on bottom. My concentration of iron oxide must be 0.34 m or 0.34 moles per liter because of that. Assuming it's completely dissolved. This one we're working backwards. It's no longer N over V equals M. Now we're saying M times V equals N. So 3.2 moles per liter. Now we do need to make sure this is in liters, or else we are not going to get moles, we are going to get millimoles. So how many liters is this? Well, when we divide by 1,000, this is 0.067 liters. When I do that, liters cancel out and I'm left with moles. Well, our hydrogen is 1, oxygen is 16, so 34 grams in 1 mole. So, if I have moles up top, I need moles on bottom. So this is going to be 34 grams of hydrogen peroxide in 1 mole. So 3.2 times 0.067, because it's on top, times 34, because it's on top. Okay, so how many grams would I be delivering? I would be delivering 7.3 grams. 7.3 grams of hydrogen peroxide. As I said, you need to be able to show your units. Showing your units will guide you in the right direction. Yes, you can break this down into smaller and smaller steps if you have to. However, I try to do the minimum amount of steps, and so with that in mind, I try to show my units at all the steps so we can see why we're going here, why we're doing there. Now, there's something we won't focus largely on, but it's something we need to take into account. Molarity of ions. Molarity is a measurement of a solute in a given solution. But when we're talking about an ionic compound, the moles we're referring to is of a formula unit. The idea is that when a strong electrolyte dissolves, it produces multiple ions, and each ion relates to the subscript. So, for example, if I have sodium chloride and I dissolve sodium chloride, I don't have 1 mole of salt atoms. I have 1 mole of sodium and 1 mole of chloride in 1 liter. How many total ions? I would have 2 moles because they've split into 2. If I had 1 mole of sodium sulfate, because of the nature of sulfate being a oxyanion but altogether, it would produce double the sodium because there's 2 sodiums to balance the sulfate, and per 1 sulfate. And so if we have a total of 3 moles of atoms dissolved in the same 1 liter solution, 3 total moles of ions in the same 1 liter solution, because of the nature of these ions breaking apart. This is only true for ionic solids. It's not true for covalent solids, but pretty much it's only true when we have metals and nonmetals mixed together. This will rarely come up, but occasionally it is of importance that you recognize the concentration of something would increase if there is 2 equivalents of it. And sometimes we will have to do concentrations involving liquids. Now, unlike in an aqueous solution, a liquid, if you give the physical state of liquid, it's assumed to be pure. But if I dissolve a given volume of a pure liquid, we can know its density, and we can use the density to convert that value into a mass. So, for example, if I mix bromine in water to disinfect a pool, the reaction that occurs is that the bromine breaks into hydrobromic acid and hypobromous acid. And so the question that we're going to ask is, how much liquid bromine would we need to treat a pool of 1.85 million liters, which is an Olympic-sized swimming pool, to a concentration of 4 milligrams per liter of hypobromous acid, assuming the density of bromine is 3.1 grams per milliliter. So we have to start from our end goal. This is the concentration density of hypobromous acid. I set this up so we don't have to use molarity of hypobromous acid. So with that in mind, 4 milligrams per liter, and I multiply by the volume of my swimming pool. That would give us the milligrams of hypobromous acid. I may want to convert that into grams, as you see there, and I guess I do in turn convert that into moles. That if I add the total molar mass of hypobromous acid, and we do that, let's say, well, we'll need 75.6 moles of hypobromous acid in that swimming pool. Well, for every 1 mole of hypobromous acid that gets formed, we needed 1 mole of bromine. So we're doing that conversion down there. And you can calculate what is the molar mass of bromine to figure out how many grams of bromine would be required. But the last step is we need to convert that, since it's the mass, into a volume by using the density. The density tells us, well, what size container? Yes, I know, absolutely, you could pour the bromine into a big beaker and weigh it out and figure out how much weight of bromine would we need to pour into the pool. But oftentimes it's easier to just calculate a volume and then just pour that volume in. Especially if you're buying it by the container, you need to know how many containers you have, and so you need to know what is the volume of that container. So it's possible to do our same dilutions with volumes by using the density, but largely we will not. We will not have to. More often than not, we will deal with solids, not liquids. The last concept that we will focus on is titration. Titration is the way that we can determine an unknown concentration of a known compound. If you have something sitting on a shelf and it's unlabeled, but you know what is dissolved in it, it is possible to find out the atomic ratio, the ratio of moles of the solute and liters of solution by use of titration. The titration works this way, that we'll take a known solution, which we're going to call our standard solution. And we're going to use a burette, which is a piece of glassware that can slowly and carefully add a volume. So we're going to slowly add the titrant. The titrant being our standard solution. The titrant is the solution that gets titrated into a solution of the unknown concentration. How this works is, if you know what's in there, you know reactions that will occur. And if you base knowledge of this reaction based on when equal molar or stoichiometric amounts have been reached, the solution is what's called the equivalence point. You've essentially reached the point where all of our titrant has reacted with all of our unknown solution. So the reaction has 100% completed. And if we can figure out that magical tipping point, it's like you have a scale. Those old-fashioned scales, you would put one object of an unknown weight on it on one side, and you'd slowly add weight to the other side until it balances. If you have weights of known masses, you can very carefully figure out what is the weight of your unknown solid. It's a similar thing. We're going to slowly add one solution until the other solution is perfectly neutralized, perfectly canceled out. And if we do that, we can absolutely know our concentration. This practice is commonly used with acids and bases, especially because acids and bases will normally neutralize themselves to become neutral water, and because we can use colorimetric indicators or a pH meter. Those are very easy ways. You can put something like phenolphthalein, and it will change color violently when it goes from acid to base, and we'll see, oh, it's done. But the one important thing to note, for this to hold true, the moles of acid must equal the moles of base. And because we're looking at acids and bases, we'll use MAVA and MBVB. But this only works in situations where we have one equivalent of base and acid. It's not going to necessarily work in something like H2SO4 or MgOH2. It becomes a much more complicated situation. So we have to worry about them being 1-to-1 ratios. Now, this last problem. If I titrate 15 ml solution of AHF by 0.125 m of NaOH, 43 mils of base, and we want to know what is the molarity of acid. And also, that's one problem. And the other one is 20 mils of NH3 is neutralized by addition of 8.2 mils of 0.95 molar acetic acid. And we want to know what's the molarity of the base. Now, you have to correctly identify which is the acid, which is the base. However, some of these have been made clear. 15 mils of HF, you may not know. You should know it's an acid, but you may not know. However, we are titrating it with NaOH. So that means we're adding NaOH to the HF. So we're adding NaOH. After 43 mils of the base is added, so we've added the base. So what have we added? We've added this. Plus, this has already been given a volume. It's already been given a volume. So that volume can only be linked here. The 20 mils of NH3 is neutralized by the addition of 8.2 mils of 0.95. You may not know that this is the base and this is the acid. However, 8.2 mils of this thing means these two numbers are intrinsically linked together. Do not separate. Do not separate. You're only going to cause yourself some problems. So with this in mind, MA is 15 mils. If the MA is throwing you off, do M1. VA, which is our V1, is unknown. Actually, being stupid. That's VA. MA is unknown. Our MB is 0.125. Our VB is 43. So, MA times 15 mils equals 0.125 M times 43 mils. Is this going to be a problem that these are in milliliters? No, because if I change that by a factor of 1,000 and I change that by a factor of 1,000, they've both gone 1,000 in the same direction. So they would cancel each other out. So I'm dividing both sides by 15 to get that to the other side. MA equals 0.125 M over 1 times 43 mils over 1 times 1 over 15 mils. Mils and mils cancel out. The math is simply 0.125 times 43 divided by 15. So my concentration is something like 0.36 M. Easy enough. Same situation. My MB is unknown. My VB is 20 mils. My MA is 0.95 M. And my VA is 8.2 mils. Once again, all I have to do is set up my equation. MB times 20 mils equals 0.95 molar times 8.2 mils. Divide both sides by 20. And what do we get? Plug this in. So 0.95 times 8.2 divided by 20 gives, what is my concentration of base? It'd be 0.39 M. And if I jump back, this is what we'll see. Okay. 39. Okay, so that is the end of this material for this chapter. So there's been a lot of math, and hopefully you can manage it, because we've gone through this slowly and trying to go as methodically as we can. Remember, units must cancel. We're always going towards the next unit. Keep that in mind. Thank you, and good day.